We are not the performers of we
Well, we didn't give it enough drama.
We've got a sluggish audience. That's the problem. And let's see if we can have some questions. Let's see if we can have some questions.
Right. So welcome everybody. Welcome everybody online for the last, right?
No, second last lecture.
What do you mean? The 2 hours?
Well, there's a break. There's a break.
The last sequence.
One is still at the break.
The last sequence of talks by Ben Knudsen. And yeah, please, stage is yours.
Thank you. Thanks for the introduction. Thanks everybody for coming back for a third long day of lecture. So the last 2 days, I hope I can be heard online. I guess they'll tell me if I can't be. Oh, thank you for telling me that you can hear me. The last 2 days, over and over and over again, I've said dimension at least 2, like 30 times I've said that, like an incantation, like a protective spell. So what I'd like to do today is
There's a question?
Yeah, I mean, this is not a question, like this is the answer from previous talk. Yes.
oh, I see.
What has happened? We can hear you. That's old.
That's old news.
So can we check?
It's unclear whether it's
Can
fake.
can the people online hear us?
Amazing. Somebody's not away from keyboard. Yeah, so what I'd like to do today is look at one-dimensional spaces and see what we can say. Okay. And for a moment, we will not be able to say anything interesting, and then we will be able to say more interesting things. So what are some one-dimensional spaces? Well, there's the real line. So let's look at the example of the real line. Yeah. So if we have here's the real line, which maybe we'll think of as the unit interval. If we have a configuration of an ordered configuration of particles, maybe they're here. Then what do we have? We have a permutation. The reason we have a permutation is that these particles are ordered in 2 different ways. They are ordered by virtue of being an ordered configuration, and they are ordered linearly going that way, right? And the difference between those 2 orderings is a permutation, okay? So maybe this is particle sigma 1, this is particle sigma 2, this is particle sigma 3, and so on. Sigma of k. Yeah, everybody on board? If we record that permutation and just concentrate on the rest of the information, then what do we have? We have a sequence of numbers between 0 and 1, non-inclusive, that cannot be equal to each other. A sequence of increasing numbers, right? That's called the interior of a simplex. It's one of the ways of coordinatizing the interior of a simplex. So was there a question over here? No? Okay. So what this tells us is that the configuration space of k ordered particles in the real line is homeomorphic to the symmetric group recording the permutation times the interior of a k simplex. Okay, recording everything else. Which of course is homotopy equivalent to the discrete space with k factorial components. Okay. In particular, if you think about the action of the symmetric group, what this will tell you is that unordered configuration space of k particles in the real line is contractible. And this sounds like it should be disappointing. Like, contractibility is one of two things. Either it means that something is boring, or it means that something you want to do is not obstructed. So this is actually kind of an important fact because it means that things are not obstructed sometimes if they look like a configuration of particles in an interval, where they would be obstructed in higher dimensions if it was a configuration of particles in a square. Everybody on board so far? I hope so. Okay. What's the other one-dimensional space that you know? The circle. Hopefully everybody knows the circle and not just Ron. So let's think about the circle. Well, the circle is an example of a sphere. There's only one way to understand a sphere. What is it? There's only one way to understand a sphere. What is it? Sphere of any dimension. Not that way. The answer, of course, is stereographic projection. So if we have a configuration, say in my picture, it will be a configuration of 3 particles. 1, 2, and 3. Then we can perform stereographic projection from the first particle. And so what stereographic projection is I look at the tangent line to the antipodal point and draw lines like so. Okay, and then what I have is now a configuration of 1 fewer particles in the tangent line antipodal to the particle number 1. Yes.
So this is marked configurations, right? What if the line? Oh, if the first one is down at the bottom.
No, so we are that's important. We're performing stereographic projection from particle number 1, and so they have to be labeled because we have to be able to say which one particle number 1 is. So this doesn't work for unordered configuration spaces. Does that answer your question? If this was particle number 1, we'd be projecting onto this line. Yeah, so we're projecting onto the tangent line antipodal to particle number 1. Is everybody on board?
If you have 2 and 3, if 3 is number 1 and 2 is like if the line between 3 and 2, as it is now, is actually parallel to the axis.
No, it's always projecting from the North Pole, no matter what.
Yeah, no, he didn't say that.
I don't understand the question. I'm sorry.
Okay, so it's marked configurations, right?
Yes.
So you have, I'm going to do a permutation. So 3 is number 1. Yes, that's going to be your number 1.
Great.
Number 2 is going to be just across from it, so there's a line between them is parallel to the baseline.
So I think what you're asking about is what if there's a particle here? And then stereographic projection sends it to the origin.
So the point itself is a fixed point.
So stereographic projection is a homeomorphism from the complement of this point onto R.
Okay, so the baseline also changes according to.
Yes. So again,
that's the point.
Again,
okay, thank
we
you.
are doing stereographic projection onto the line, the tangent line, antipodal to particle number 1. Yeah. Okay, great. Other questions? Okay. So what this tells us is that the space of configurations of k particles in the circle is homeomorphic. So if we were in a higher dimensional sphere, we'd have to worry about the fact that these tangent fibers are changing. And so we'd have some kind of fiber-wise configuration space. And that's a totally valid description. Fortunately, the circle has a trivial tangent bundle. Yes. And so I can just trivialize it and say that it's a copy of the circle for particle number 1 times, what do I have? I have an ordered configuration in R of one fewer particle, right? So fk minus 1 of R, once I've identified all the tangent fibers with R. And we just learned what this is. So this is homotopy equivalent to a disjoint union of k minus 1 factorial circles. Sorry?
We were missing the point.
Fear not, it was pointless. Okay, so a disjoint union of k minus 1 factorial circles. This is not an equivariant description because we had to privilege particle number 1, but if you do a little bit more work, you can come up with an equivariant description that will imply that the unordered configuration spaces of the circle are all homotopy equivalent to circles themselves. Okay. And that's the end of the lecture. That's all the one-dimensional manifolds there are. So we're done. So the upshot of these two examples is that configuration spaces of one-dimensional manifolds are super boring. There's no reason you would ever study them ever, because these are what they are. Questions so far?
What if I think of the circle as the manifold RP1 and I work out the configuration spaces of RP1? Is that a homotopy invariant? Am I going to get the same answer?
RP1 is homeomorphic to the circle, so you will definitely get the same answer.
Okay. So,
those are the same space. I don't know the difference. It's possible I don't understand your question, but
how do we know that the configuration spaces are topological invariant of this? How do I know if M1 is homeomorphic to M2, that the configuration space of
everything in topology is homeomorphism invariant. That's the definition of topology. The definition is take the Cartesian power. That's homeomorphism invariant. Remove the fat diagonals. That's homeomorphism invariant. Yeah. Okay. Great. Other questions? Yeah.
What if I take non-paracompact one-dimensional manifolds, like the long line?
Never,
Never
ever do that. Don't do that. Yeah. So, that's a great question. So one answer is I don't believe in non-paracompact manifolds. It's not a good idea, or oh, sorry, paracompact. I thought you were saying non-Hausdorff. That's a really bad idea. Then configuration spaces don't behave well at all because like things can like kind of collide at the two origins, but not really. You know what I mean? So it's a bad situation. I haven't thought about non-paracompact manifolds at all, like since I took Munkre's topology class as an undergraduate. So this is a question that you probably know the answer to, but I don't. Yeah. Other questions? Okay. Great. So here's an example. Here's another example. This is the simplest example of a one-dimensional space that is not a manifold. So it is this graph. This is sort of the minimal example. Here is something that you can do with two particles on this graph. Here they are. Number 1 and number 2. You can move particle number 2 onto the unoccupied edge through the essential vertex. I'm going to probably, without thinking, use the word essential to refer to a vertex. That means valence at least 3. So I'm moving this particle through the essential vertex, and now this leg is free, and I move the particle number 1 onto that leg. And that gets me a picture that looks like this. where particle 2 is there and particle 1 is there. And then I can do basically the same thing. I can move particle number 2 over here and particle number 1 over there. And that will get me a picture that looks like this. And then I can do it one more time. Move particle 2 here, move particle 1 there. And the end result will be the same configuration that I started with. Yeah. So these are 3 paths in the configuration space of 2 particles on this graph. If I concatenate them, then what I get is a loop, because the starting point and the ending point are the same, right? So this picture is a description of an embedding of the circle into the configuration space of 2 particles on this star-shaped graph, which I will call S3, lower script S3 star. Okay. Yeah, everybody on board? The exercise for you is that this loop is essential, not null homotopic. So this loop is essential. As a hint, as is depicted by the blackboard, this graph embeds into R2, and we know a lot about configuration spaces of R2. Okay, so we know there's at least one hole in this space. Great, that's progress. Unfortunately, we started with an example like this with at the very, very beginning with Rn and 2 particles, and then we were like, let's do an inductive thing. And then I wrote down the Fedal-Neuwirth vibration, and then we were off to the races. We had an inductive approach to the configuration spaces. And that approach just totally breaks down, because the coordinate projection from the configuration space of k particles to the configuration space of k-1 particles is never a fibration, as long as the graph is not a manifold. So maybe I will say that out loud as an exercise. Think about it if you want to. If a graph has an essential vertex, then the coordinate projection is not a fibration. Nevertheless, one of the conclusions that we drew from the Fedal-Neuwirth fibration is still true for graphs. So this is a theorem. I'm going to write all 3 names because I'm not sure who wrote down the first proof without a mistake. So Aaron Abrams, Rob Greist, and Sviatkovsky. I think the diacriticals are there and there. It's always difficult for me to remember. So the theorem says that for any graph, both the unordered and the ordered configuration spaces of the graph are aspherical. No higher homotopy groups, k pi 1. So as with most surfaces, in particular with R2, when we study configuration spaces of graphs, we are secretly doing group theory. We're studying their fundamental groups, which are called the graph braid groups, or in the case of the ordered configuration spaces, pure graph braid groups. These are the perhaps pure graph braid groups. And when we say things about their homology, as we will, we are saying things about the group homology of those groups, which are interesting, for example, to geometric group theorists. Perhaps I should have said maybe one other thing about one other motivational thing, although we are taking Cohen's axiom to heart and studying configuration spaces because they're interesting. The original motivation for thinking about configuration spaces of graphs came from thinking about problems from robotics, thinking about motion planning problems where you idealize robots or self-driving cars or something like that as points, and you idealize the mechanical systems that they're moving on as graphs, And then you try to study the motion planning problem by studying the topology of configuration spaces of graphs. That's somehow the original motivation. But I'm not going to say anything about that. So we have this theorem. And so the question now is, we know that the fundamental group of this space is not trivial because this loop is not essential because you did the exercise. Good job. And so the question is, which non-trivial group is it? Okay. So the idea, which is one of two ideas that we will sort of squeeze for all they are worth, is that near an essential vertex of a graph, it kind of doesn't matter where the particles are. By which I more precisely, well, I guess that's precise enough since this is just an idea. So I'll just say the exact positions of particles don't matter. So why would that be the case? If you have a graph, you can lay it on the table. And if it has an essential vertex, you can grab the essential vertex, you can lift the graph up into the air, holding the essential vertex. And then what will happen is that particles will fall under the influence of gravity away from that essential vertex that you're holding, right? So here's a local picture of a graph. There's the essential vertex. Here are my the edges that are emanating from that essential vertex. And maybe I have particles. 1, 2, 3. They can be ordered, it doesn't matter. And what we can do is we can just let them go until there's at most one left in this picture. One left in the open star of this vertex. Okay. So to make a somewhat precise statement, which we made more precise, or this is perfectly precise, but it will be made more general later as an exercise, you can think about why do I want to, okay, let's say it that way. It doesn't matter. So we can look at the subspace of the configuration space of two particles on this star graph that we're trying to understand. Oh, you have a question, I'm sorry.
Maybe I missed it, but those particles, they can walk off because it's like open? Is that why?
Yeah.
Okay.
So the subspace of the configuration space of two particles in S3, in which at most one particle is in the open star of the essential vertex. Sorry, I actually want to say something. I want to say something stronger, and you can think about how to take this idea and make it real for this stronger claim. I want at most one particle in the open star of any vertex, including the univalent vertices. It's in, well, okay, whatever. That subspace is a deformation retract. is it questions about the statement? It took me a minute to get it out, so it might have been confusing. Okay, so what is that subspace? So here's the graph. And let's number the vertices. Here's vertex 0, 1, 2, and 3. And so an example of something you are allowed to do in this subspace is a particle is allowed to stay stationary at vertex number 1, while another particle, I guess we'll call that particle 1, while the second particle is allowed to wander freely along this edge. Particle 2 can do that without violating the condition on at most one particle being in the open star. It could also wander freely along this edge, no problem. Okay. I'll draw that. I'll call this position, changing my mind about which is, it doesn't matter. If I don't match my notes, I'll be confused. I'm going to call this position 1, 2, because particle 1 is at vertex 1, particle 2 is at vertex 2. I'm going to call this position 1, 0, because particle 1 is at vertex 1, particle 2 is at vertex 0. Okay, so there's what looks like an edge connecting those two positions. So let's draw that. This is an edge connecting position 1, 2 with position 1, 0. Okay. Where else could you go from 1, 2? The only other place you could go from 1, 2 is you could move the first particle along this edge. So that would be an edge connecting 1, 2 to 0, 2, where particle 1 is at 0 and particle 2 is at 2. And from this position, the only other thing you can do then send this particle this way, because it can't go here without encroaching on the open star of that vertex, is to send it over in the direction of 3. Right. Okay. And so there's an edge connecting over to what we would call 1, 3. Is everybody on board? No. So the fact that the first coordinate is 1 means that particle 1 is stationary at vertex 1. Particle 2 is moving between 0 and 3. Does that answer your question? Okay. Okay. So you can think about what the other various possibilities are, and what you will get is a sort of I think I probably am not going to have drawn this very beautifully when I am finished drawing it, but that's okay. Okay. It's a very ugly Star of David. Great. This is 1, 3. This is 0, 3. This is 2, 3, 2, 0, 2, 1, 0, 1, 3, 1. 3, 0, 3, 2. Okay. Is anybody not 100% sure what this picture is showing? Okay. And so this is a picture showing the subspace in which at most one particle is in the open star of any vertex. And what the exercise says is that this is embedding as a deformation retract into the configuration space of 2 particles in S3. Okay. So the non-trivial group that pi1 of this space is is the integers, because that space is a circle up to homotopy. Yeah? Questions about any of that?
Where is S3? In this proof by picture.
Where is S3?
If you're trying to get an essential mapping, that's to S3.
S3 is,
S3.
Subscript, not superscript. Is there a name for dyslexia except up and down instead of left and right? Okay, we can do a little bit better than this example, which is not particularly topologically interesting, although it is actually sort of the fundamental example in the same way that the configuration space of two particles in Rn is the fundamental example for manifolds. Is there a question? So let's look at a more complicated graph. Let's look at K5, the complete graph on 5 vertices. This is K5. We can, you can think about why this deformation retracts onto the subspace where no particle is in, at most one particle is in the open star of any vertex. One thing I will emphasize is that only these are the vertices. These crossings are not actually there. This is a non-planar graph, so I can't draw them without those crossings. Okay, so let's try to do a similar analysis for this space, for the configuration space of two particles on this graph. I won't be able to draw the whole thing because it's too large, but we can draw a local picture. So let's draw a local picture near near the vertex 1, 2. Okay, so I should number these. So there's 1, 2, where particle 1 is at vertex 1 and particle 2 is at vertex 2. Something I can do now in this graph that I couldn't do in this graph is I can move this particle along this edge and this particle along this edge freely without interfering with each other. Right. So what that means is that locally at 1, 2, I see a square. Right. So this is a square that goes from 1, 2, 1, 3, 4, 3, 4, 2. Is anybody not 100% sure what this is supposed to be showing? This isn't everything you could do from the vertex 1, 2. You could also move along many of the other edges, right? So if you perform the same kind of analysis, the kind of picture that you draw looks like this. Maybe I can draw it slightly prettier than I did last time. Unlikely. I won't bother labeling all of the vertices. So this is a local picture near the vertex 1, 2. This is sort of all of what you can do from the vertex 1, 2. Is everybody on board? There's more stuff, but it's not accessible. Yeah. This is a picture of a homeomorphic copy of the unit square. So the shading means that there's stuff there. Yeah. Other questions? So does anyone notice anything about this situation? is a local picture at 1, 2. What can you conclude? Sorry? It looks, yeah, so what's that called? It's a manifold. Okay, so the configuration space of two particles on K5 deformation retracts onto a surface, compact. It's easy to see it's compact. You can think a little bit and see that it's orientable. And you can do some combinatorics to count vertices, edges, and faces to see that the Euler characteristic is -10. So the genus is 6. Sorry, I'm writing below the line. I apologize. I'll raise it temporarily. Okay. So just to go through it one more time, the space deformation retracts onto the subspace where at most one particle is in the open star of any vertex. Locally, that space is modeled in this way. So it's a surface. It's obviously compact. You can think about why it's orientable, and you can count easily to see the Euler characteristic is -10. Okay. So the configuration space of two particles in K5 is a K-pi1 for this surface group. Questions about, yeah.
So you drew a picture on the bottom board and a picture on the top board, and one is like the boundary of the other. Is there some like good reason, like some way I can see that from the graphs?
Is there some good reason? Yeah, so I guess what I would say is the comparison between the two is going to be telling you that you can produce some embedding of this graph in this graph and push this loop, this homology class forward, or homotopy class forward into this space, and it will be null. Yeah. I don't know if that's the kind of answer you wanted, but that's all I can think to say. Other questions?
Following on that, the embeddings of the graph above into the one below, does that give you an embedding of the star into your manifold? See, there are embeddings of that thing up there into the bottom.
Yes. I think the answer is yes.
Yeah.
If I understand what you're asking. Other questions? Okay, so I'd like to state a result that generalizes this exercise and makes this idea about vertices sort of official. So this is a proposition which in this form is roughly a result of Agarwal, Banks, British, and Miata. The difficulty of the result is less than the number of authors, but by far. So if we have any graph and a set of its vertices, the configuration space, ordered or unordered. Oh, sorry, I forgot a clause. So what you would want to write is that the configuration space deformation retracts onto the subspace where at most one vertex is in the open star of any of the vertices in W. That's not quite true, but you can fix it by subdividing the graph, which doesn't change the homeomorphism type of the graph, and so it doesn't change the configuration space. So not a big deal. So there's a subdivision. Gamma prime, by which I mean you just add some bivalent vertices to the graph. With the property that the configuration spaces of gamma, which are the same as the configuration spaces of gamma prime, deformation retract onto the subspace of maybe I'll name it. So the name will be configuration space sub W, the name of the set of vertices. In which at most one particle is in the open star of big W. Okay, so this is saying that if you choose any set of vertices in your graph, you can always push all but one, maybe one particle outside of a small neighborhood of each of those vertices. And this fudging about the subdivision is just to get the neighborhood small enough. Yeah.
Just to be certain, are we saying that there's at most one particle in the open star of each vertex in W, or in like W as a whole?
Right. I guess a priori those could be different.
Mhm.
Let's say, no, I'm sorry. Now I understand what you're asking. Each W.
Okay, perfect.
Thank you. Yeah, great. Other questions? Okay, so we're going to use this to great effect soon. What I want to emphasize before we move on is that the level of subdivision that you need, it doesn't depend on the number of particles. It's just one choice of subdivision for the graph, and it works for all k. So it doesn't sort of grow with complexity. Okay. So to use this in the way that we want to, we need one more idea. So the first idea was that you can be fuzzy about your idea of where particles are near a vertex. The second idea is that you can be fuzzy about your idea of where particles are on an edge. Yes. So open star is calculated in gamma prime, the subdivision, not in gamma. Does that answer your question?
Maybe you can repeat the question.
Oh yeah, sorry. I don't 100% understand the question. The question was probably something is empty if you have a large number of particles, so surely the subdivision depends on the number of particles. That was the question. Yeah.
I guess my question is, does the subdivision gamma prime depend on K?
No.
Okay.
On edges.
If you have a follow-up question, I would be happy to answer it, but the answer to your question is no. Okay. So the second idea as I said, is that the exact position of particles on edges doesn't matter. So the exact position of particles on an edge does not matter. Why is that? You all now know why that's true. Exactly. So the edge is an interval, and we learned that the configuration spaces of the interval are contractible. Okay. So if we combine those two ideas, then we can prove a theorem due to Tchaikovsky which will be the main calculational tool that we will use. So it says that the homology of the, again, I'm using the same notation from yesterday and the day before. This is the disjoint union of all of the unordered configuration spaces of gamma, thought of as a graded space. That homology is isomorphic to the homology of a certain complex. So now let me tell you what that complex is. So its name is S of gamma, S for Tchaikovsky. And it has the following form. It as a module, it has a factor of the polynomial ring generated by the edges of the graph. So E is the set of edges of the graph. And I tensor that with a tensor product, one for each vertex of the graph. V is the set of vertices of the graph of a module that I'll call S of little v, that I'll tell you what that is in a second. So far, I still have to tell you what this is, what the differential is, and what the grading is. So what S of v is, it's a free abelian group generated by a symbol called empty and a symbol called the difference between two half edges. So a half edge of a graph is like an end of an edge where it attaches to a vertex. Every edge has two half edges. Yeah. Or in other words, if you want sort of a mathematical definition, take a sufficiently small neighborhood of a vertex, remove the vertex, the half edges are the connected components of that. Okay. If the graph is sufficiently subdivided, whatever, doesn't matter. These H's are half edges at the vertex V. So H and H prime are contained in the set of half edges at V, which I'm calling H of V. So E is edges, V is vertices, H is half edges. The bigrading, which tells you which part of this complex is in what homological degree and which part of this complex is talking about which cardinality of configuration, is the following. So the degree of an edge the way we think about an edge is that it represents a single particle sitting on an edge, just sitting stationary on an edge. The reason this is the polynomial ring generated by the edges is that you could have like two particles sitting on the edge, and that would be represented by that edge squared. So that means if we think geometrically, the bigrading of an edge should be 0 homological degree because it's a particle sitting and not moving, and 1 cardinality degree because it's one particle. By degree of the symbol empty, the way we think about the symbol empty is that it represents no particles occupying that near that vertex. So that's a homological degree 0 description and also involves no particles. So the bidegree of empty is 0, 0. And the bidegree of a half edge, the way we think of a half edge is it represents a particle moving into or out of, depending on your convention, the vertex along that half edge. So that's a homological degree 1 description because it's a path, and it's a cardinality degree 1 description because it involves one particle. So the bidegree of a half edge is 1, 1. And then both degrees add under tensor products in the usual way. Okay. Yeah.
So when you say that it's the homology of, that's an algebra, the S gamma?
No. So a priori, I'm just describing a bigraded chain complex.
A what?
A bigraded chain complex.
Okay.
Um,
Right. Okay. Right.
It does, I haven't told you the differential yet. It does have the structure of a differential graded module over this ring. That's extra structure, but I'm just telling you a bigraded chain complex. And the differential, let's draw a picture to try to see what the differential sort of has to be. Let's look near the vertex V. And the differential on an edge should be 0 because it's a stationary, it's not moving, or it's a degree 0 thing if you like. So its boundary should be negative degree, and so 0. Similarly with this. So really, to tell you the differential, because I'm tensoring a bunch of things together, I only need to tell you its value on a half edge, or rather on a difference of half edges. So what we said about a difference of half edges is that what we said about a half edge is that it represents a particle moving into the vertex along the half edge H. This is the vertex V, this is the half edge H, and this is the half edge H prime. So the difference represents this movement, like that. Okay, and if I take the boundary of that, clearly I should get, oh, sorry, I think I made the wrong convention when I said out loud just now. This is the half edge H, and this is the half edge H prime. Let's say that. Okay. So we should get the difference of two things: the difference of the endpoints of that path. And if we do that, then what we get is a particle here sitting on the edge associated to the half edge, minus a particle sitting here on the edge associated to the other half edge. Okay, so the value of the differential on a half edge is a difference of two edges. And that determines the differential everywhere. So d of H minus H prime is the edge associated to H minus the edge associated to H prime. Every half edge has an associated edge. This is a little, kind of a lot of baggage. Please ask any questions that you have about that baggage, and then we'll prove it. Yeah.
So for every vertex, you have a different empty set.
Yes. Yeah. So strictly speaking, we should call it empty sub V, but well, we're not really going to use the notation at all. But when we actually use the notation in practice, we just drop these from the notation entirely.
Right. And then when you say that the H and the H prime model that picture over there, you have actually four. It's a 4-valent vertex there. So
Yes.
let's make a difference where you go.
Absolutely. So the rank of, like, I have 4 half edges at this vertex, and so I have 3 differences of half edges. Right. And so I have a rank 4 sort of local module, 3 for the differences of half edges, and yeah. Other questions? Yeah.
Would you be to just explain again what the difference of the half edges is representing?
Yeah, so the difference is, so one half edge by itself represents a particle moving along that half edge. So the difference of half edges represents particle moving into the vertex and then out of the vertex along those 2 half edges. It's a path. Yeah. Other questions? Sander, I saw your hand. Do you have a question? Oh, yeah. Okay. So let's prove it. And then maybe we'll take a break. So let's prove it. So we're going to use the proposition, and we're going to take W, the set of vertices that we want to repel particles away from, to be the set of all vertices of gamma. So take W to be the set of all vertices. And what we're going to do is, well, so then what we know is that there's a subdivision of gamma prime, and the configuration space deformation retracts onto the subspace where particles are repelled from the vertices of the original graph. And we're going to filter the configuration space of, or rather this subspace, which is a deformation retract. By subspaces, which I will call X sub S. And X sub S is the subspace in which at most S particles lie in the open stars of those vertices, in the union of the open stars. Okay, so there's at most 1 particle in the open star of each of the original vertices, and we can just count how many of those open stars do have a vertex. And that's our subspace. Okay. Then there will be a spectral sequence that arises from that filtration, which is where this complex will come from. And what is relevant for the spectral sequence is the homology of the associated graded. So what's the associated graded? Well, what is this quotient? What we're saying is that we have at most S particles in the small neighborhood of the set of original vertices. And we're quotienting out the subspace where we have S minus one of them, or fewer than S total, right? So what does such a configuration look like? Well, I'll just write the formula and then we can talk about it. So I have K minus S particles in the complement of that set of vertices. And then I have to choose from among the vertices, S of them to have a particle. And then I have to say where in the open star the particle is, right? So that means I will be taking a wedge over subsets, what do I want to call them? I guess I wanted to call them capital S. Subsets capital S of W of size equal to little s. And then for each of those vertices, I have to choose the position of the particle. So I have to smash over the vertices in my subset S with the space of positions of that particle. And the space of positions of that particle is a star of valence equal to the valence of that vertex, except at the boundary, it goes to the base point. So that's a star of valence, the valence or degree of V modulo the boundary of that star. Yeah.
Is there a subscript that I on the BK minus S?
Sorry?
Like, is there a subscript on the BK minus S all the way to the right?
Oh, yeah, that's a plus.
Okay, okay. We're adding.
Adding a disjoint base point, yeah.
Oh.
Mhm. Okay. So then let's interpret this. It looks slightly fearsome, but it's actually made of extremely simple pieces. I'm taking gamma and I'm removing all of the vertices of gamma. So that's a disjoint union of intervals. Great, we know, we can understand this. This is now therefore a disjoint union of products of it's a union of contractible components. Okay, whatever. This is also not so bad. This is a cone on a finite set modulo its boundary, so it looks like an egg beater. So it has the homotopy type of a wedge of one fewer circles. And so I'm smashing a bunch of contractible things against a union of smash products of wedges of circles. So in other words, all of this is going to end up looking like spheres, right? Bunch of spheres. What's the dimension of those spheres that are going to show up? Well, the only thing contributing to the dimension is this smash product. And there are S many factors of that smash product. And the circles being smashed together are one-dimensional. So this has the homotopy type of a wedge of S-dimensional spheres. So in grading S, the associated graded has the homotopy type of a wedge of S-dimensional spheres. This has the homotopy type of a wedge of S spheres. And so what can we say about the spectral sequence that arises? Well, it looks exactly like the spectral sequence that comes from the skeletal filtration of a CW complex, where the associated graded is is a wedge of spheres in dimension equals filtration, right? And so what that tells us is that the resulting spectral sequence is concentrated on the first row. And so it collapses after D1. And D1 is the only differential that you can actually understand in a spectral sequence. And the form of this complex and this differential comes from thinking about the combinatorics of that associated graded expression. And this differential comes from just looking at the definition of D1. So that's all I'm going to say about the proof. There are, of course, lots of details to unwind, but at this point, it's an exercise that you can do. Okay. I think this is probably a good time to take a break, but I don't want to squash any questions that people have. So are there questions that people have? Yeah.
Is there a reasonable similar description for the ordered configuration space? That
Yes.
maybe be as an invariant.
Yes,
equivariant?
you just
Okay.
need to like put permutations everywhere. Yeah. Maybe I will make one comment before we break. This is not Sviatkovsky's proof of this theorem. What Sviatkovsky does is Sviatkovsky constructs a deformation retraction onto a cubical complex that's a subspace of the configuration space. And this complex is cubical chains on that subspace. Cool. So let's take a break and let's resume at 3:52. 15 minutes and 15 seconds from now.
You learn anything if you take gamma to be an n-gon, and then you just increase n, take some sort of colimit of configuration spaces. Do you end up with something?
No, so the configuration spaces are topological invariants. And so the n-gon looks the same from the eyes of configuration spaces. There's like
it's a graph. The n-gon is a graph.
Yes, so
This answers
this complex will be more complicated as n increases, but it will produce the same answer.
Or n is buried in the vertices there.
Yes, that's right.
Okay, so